All right, so let's talk about energy. Energy, we all have an idea of what energy is, and it's an important property of matter. From a chemist standpoint, we can think of energy as just a property of matter, and it's related to the motion of atoms and molecules. So what we're going to try to do today is we're going to take a look at energy from the point of view of atoms and molecules. And okay, so it's something that's related to the motion of atoms and molecules. And so when we're doing this, what we're doing is we're doing what's called physical chemistry, or the physics of atoms and molecules. So anytime we're talking about motion and energy, we're dealing with a branch of science known as physics. So when we talk about motions of atoms and molecules and their energies, we're talking physical chemistry, or atomic and molecular physics, or you can call it chemical physics. Okay, so I'm a physical chemist, okay, and I could also call myself a chemical physicist. If the focus of your study is this, then you're a physical chemist or a chemical physicist. Whether you're called a physical chemist or a chemical physicist depends really on what your undergraduate degree is. If you have a chemistry major and you specialize in this later, you're a physical chemist. But if you're a physics major and you specialize in this later, then you're a molecular physicist or a chemical physicist. So anyway, understanding energy helps us understand behavior of atoms and molecules. So let's start with the basic ideas from physics about motion and how to describe motion and why things move. And then we're going to talk about energy as a way of summarizing, or a good way to visualizing motion. Okay. Position, let's start with the idea of a position. A position is an example of what's called a vector. A vector is something that can be defined by specifying a magnitude and direction. So you need to specify two things to define a vector. Now, position is an example of one. To locate something, first thing you need to do, though, is you need to have some kind of reference point. Because if I ask you, where are you? You can't just tell me 10 meters away. You have to tell me 10 meters away from what? Okay, so the reference point is the origin. Okay, and so you have to specify the reference point and how far it is from the origin, and the direction you have to take to get there. So these are the two things you need to specify that particular vector. So if I draw a number line here, I call this point my origin. I'm going to call that 0. Then that's my reference point. So we're just going to focus for now on just motion on a straight line, just to get the basic ideas out. Okay. Of course, you realize we live in a three-dimensional world, so you actually need more than just one. You're going to need more than just one number to locate something. So you pick a point on the line. Let's say you have an object moving on the line. So you pick a point on the line where the object is. Let's say an object is at this point. Okay. And we're going to call that location X. All right. And we're going to say this distance right here is D. Then X over here is equal to positive D. Okay. And if you say it's 5 meters away to the right of 0, you can say this location is plus 5 meters. And if you say it's the distance from the origin is 5 meters, but it's on the left side, then we say X here is going to be negative D. You say, let's say it's 5 meters to the left, then you say the location is negative 5 meters. Okay, now which direction you call positive and negative is really arbitrary. As a matter of custom, people just say if we go to the right, I call that the positive direction. Going to the left is the negative direction. But that's really completely up to you, as long as you use it consistently. Okay. So that's how you specify a location. You say how far, that's the distance, and which way. To the right, you give it a positive sign. To the left, you give it a negative sign. Now, displacement is a change in location. So we say something is moving if it changes location. And so for one-dimensional motion, when I say one-dimensional, we're just talking about motion on a straight line, okay? Because, like I said, we live in a three-dimensional world. You have to specify actually which way right, which way north-south, which way up and down. So that's 3 dimensions to specify an actual location. So like I said, we're just going to focus on one-dimensional motion. So the displacement is defined as the difference in the final location, x2 in this case, minus and the initial location. So x2 minus x1, that's called the displacement. Final location minus initial location. So you could say that x2 is the location at time t2 and x1 is the location at time t1. This letter here, delta, Greek letter delta, it looks like a triangle. That means change in. Okay? So anytime you put that in front of a symbol, that means change in whatever the symbol is. Delta x means change in x. So, for example, if an object moves 3 meters to the left, what's the displacement? It moves 3 meters to the left. So let's say this is 0, -1, -2, -3. What's our displacement? The displacement is, let's see, delta x would be, the final location minus the initial location would be -3. Okay, so now that's assuming we take movement to the left as the negative direction. Like I said, that's really all up to you. As long as you do it consistently when you solve problems, you have a series of calculations to do. You just have to be consistent with it. Now, if let's say this was at 5, you move 3 meters to the left, so there you go, 5, 4, 3, 2. So you go from x equals 5 to x equals 2. What's our delta x here? It's still going to be -3. So you have 2, final location, minus the initial location is 5. It's still going to be -3. Okay, and it should be in meters, okay, since it's given to you in meters. Now, if the object doesn't change direction while it's moving, then the distance traveled will just be the absolute value of the displacement. So if something moves 2 meters to the right, okay, and then 3 meters to the left, what are the displacements for each leg of the trip? Delta x for the first step would be 2 meters to the right, so I'm just going to say that's plus 2.0 meters for the first step. And then it moved to the left, so delta x for step 2 would be -3, since it's moving to the left, -3.0 meters. Okay. What's the total displacement? I'm just going to add up these. So plus 2 plus -3 would be -1 meter. What does this mean? Well, you move, okay, here you are, all right? 1, 2, 3. Okay. So you move 2 places to the right, 1, 2, and then you move 3 places to the left, 3 meters to the left, 1, 2, 3. You end up 1 meter away from where you started, so you say your displacement is 1 meter from where you started, but it's on the left side, that's why it's negative. So that's how you would interpret those numbers. Okay? All right. Now, speed is a description of how fast an object is moving, so the average speed is obtained by simply dividing the distance traveled by the amount of time that has elapsed. So suppose an object travels 10 meters in 2 minutes. Calculate the average speed. So we say the average speed, S, is the distance traveled, 10.0 meters, divided by 2.0 minutes, elapsed time. So that gives us, how many sig figs should I have in my answer? Should I write this as 5, 5.0, 5.00? How many sig figs? 2 sig figs, very good. So 5.0 meters per minute. So that would be your unit. Now, why is this thing called average? It's called average because it doesn't mean you're moving at that speed all the time. It's just like you're saying that if you traveled traveled 30 miles in 1 hour, it doesn't mean your car has been traveling at 30 miles per hour at all times. You may have sped up at some point in your trip and slowed down. Okay, so what we call the speed, or the instantaneous speed, would be the speed that you can calculate if you were to imagine a very, 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 very short period of time. Okay, imagine a very, very, very short period of time, and then imagine how far you would have traveled during that period of time. If you take that distance that you would have traveled for that very, very short amount of time, so divided by that very short amount of time, that is what you would call your speed, or your instantaneous speed. And that's what the speedometer on your car would be telling you. Okay, so if you just have distance traveled divided by the actual time it took to make that travel, that's called just the average speed. Velocity is synonymously used with speed, but unlike speed, this velocity is a vector. Okay, and because you have to specify the velocity, in addition to specifying the speed, you have to specify the direction. So if you say you're moving 5 miles per hour, you're saying the speed. But if you say I'm moving 5 miles per hour in this particular direction, then you're specifying the vector. Now for one-dimensional motion, it's just customary to just say if you're moving one way, well, we're going to call that a positive velocity. If you're moving the other way, we're going to call that a negative velocity. And just like displacement, it's customary to just say if you're moving to the right, it's positive. You're moving to the left, it's negative velocity. Or if you're moving upwards, we can call it positive velocity. If you're moving downwards, you can call it negative. But again, that's arbitrary. Okay? So if you have an object that is a velocity of negative 5 meters per second, what's the speed? Speed in this case would be whatever the magnitude is. So what's the absolute value of negative 5? It's just 5. So 50 meters per second. Which direction? Well, whichever direction you want to call the negative direction. Okay? So if you want heading north as your negative direction, then that's what it is. If you want heading left as your negative direction, then that would be the direction. So it depends on how you define your directions. Now, acceleration. If the velocity is changing, okay, the velocity of an object is changing, we say it's accelerating. It's experiencing an acceleration. So the average acceleration is the change in velocity divided by the elapsed time, the change in time. Okay, so the unit for acceleration, as you can see here, would be the unit for the numerator. A unit for velocity is meters per second, and then the unit for time is seconds. So the unit for acceleration is meters per second, or meters, okay, per second, or meters per second squared. Okay. So true or false, an object moving at constant speed is not accelerating. That's the answer. Is that true or false? Okay. It's not true, because you can be moving at constant speed, but you could be changing direction. For example, you could be going around in a circle. You're changing direction all the time, but you could be moving at constant speed there. That you're still accelerating. Okay? So acceleration refers to a change in velocity, not just speed. If you're changing direction, you could still be accelerating, even if you're not changing your speed. So make sure you get that clarified. All right. So let's look at some examples of acceleration. Acceleration and velocity have the same algebraic sign. So if you take one particular direction as positive, and if you're speeding up in that direction, you'll find that your acceleration and velocity will have the same algebraic sign. Okay? So let's look at an example here. You have an object moving in a straight line, speeds up from 4 meters per second. So from 4 meters per second, it's now moving at 8 meters per second 4 seconds later. What's the average acceleration? Let's calculate. Average acceleration is delta V over delta T. All right, so the final speed is 8 meters per second. So we're going to take going to the right as a positive direction. So positive 8.0 meters per second is your final speed, final velocity, minus positive 4.0 meters per second is your initial velocity, okay, divided by the amount of time that has elapsed is 4.0 seconds. So 8 minus 4 divided by 4, that's 1.0. So that's positive 1.0 meters per second squared. So you'll notice your acceleration is positive and your velocities are also positive. So if you're speeding up in a particular direction, okay, the velocity, if the velocity is positive, so is the acceleration. Now, let's assume that that direction is actually negative, okay? So we're going to say our initial velocity then would be, let's just take this as the negative direction. So your velocity is negative 4.0 meters per second to begin with. And then later, your velocity, your final velocity, so V2, is negative 8.0 meters per second. If you're to take that direction as the negative direction, what's our acceleration? You're still speeding up in that direction, but what's our acceleration here? Our final velocity is negative 8.0 meters per second minus our initial velocity is negative 4.0 meters per second. Divide that by the amount of time that has elapsed, which is 4.0 seconds. And we get negative 8 minus negative 4 is negative 4.0 meters per second over 4.0 seconds. You get a negative acceleration, negative 1.0 meters per second squared. Okay? You'll notice velocity is negative, acceleration is negative. That means you are speeding up in that negative direction. Okay, so when acceleration and velocity have the same algebraic sign, that means you're speeding up in whatever direction you've taken as positive or negative. Okay, so acceleration is negative, but the velocities are negative. Here, you're speeding up in the positive direction, acceleration is positive. What if you're slowing down? What you'll find if you're slowing down is that your acceleration and your velocity will have opposite algebraic sign. Let's look at an example here. What if an object is moving in a straight line? So it's starting off, okay, we're going to take this as the negative direction going this way. So you're starting off at negative 4.0 meters per second. Okay, so you're moving at 4 meters per second to the left. So that's what, we're going to take that as our negative direction. Now, 2 seconds later, you're now moving only at 2 meters per second. So your final velocity is negative 2 meters per second. Again, that's a negative direction. So you're slowing down, okay, from negative 4 meters per second to negative 2 meters per second. Let's verify that our acceleration in this case is not going to be negative, but it's going to be the opposite. We'll have an opposite algebraic sign. So acceleration in this case would be the final velocity, which is negative 2.0 meters per second, minus the initial velocity, so this is your final, and that's your initial velocity, negative 4.0 meters per second, divided by the time that has elapsed is 2 seconds. So what does that give you? Negative 2 minus negative 4 is positive 2. So you have positive 2 meters per second is the change in velocity divided by 2.0 seconds. Your acceleration is positive 1.0 meters per second squared. So you can see your velocity is negative, your acceleration is positive, you are slowing down. And you can work it out the same way if you take the other direction as your negative direction. It doesn't really matter. Okay? So acceleration and velocity have the same algebraic sign if it's speeding up. If you're slowing down, they have opposite algebraic signs. Okay, if you're changing direction, you're also going to have opposite signs for your acceleration and velocity. Because how can you change direction? You have to slow down first, right? So if you have to slow down to stop and then turn around, and then you're changing the algebraic sign, your final velocity. You'll end up having a opposite sign for acceleration and velocity. Let's look at this example right here. You have a molecule moving at 500 meters per second towards the wall. So let's make this our wall. So this molecule is approaching the wall at 500 meters per second. So we're going to take their initial velocity to be positive 500 meters per second. Okay? And then collides with the wall, and then sometime later it's now moving away from the wall. And so a tenth of a second later, let's say, it's now moving away from the wall, moving at a final velocity of final speed of 500 meters per second. Okay, so our final velocity is now negative 500.0 meters per second. Why negative? Because it's the direction is now opposite of what we considered the positive direction. Our original direction is the positive direction, so if it's moving the other way, it's going to be the negative direction. So our final velocity is going to be negative 500 meters per second. So during this time interval, let's calculate the acceleration of our molecule. What will we do? Acceleration is your final velocity, which is negative 500.0 meters per second, minus the initial velocity is 500 meters per second, positive. So you'll notice the speed has not changed. All it did was switch directions. Okay, divided by the acceleration, which is 0.10 seconds. So the acceleration of our molecule would be what's negative 500 minus 500. That's negative 1,000 meters per second, divided by 0.10 seconds. What's my answer here? It's 10,000, right? So negative 10,000 meters per second. How many sig figs should I have here? 2. Very good. 2 sig figs in the denominator, 5 in the numerator. So my last sig fig is this 0 right here. So it's better for me to write this as 1, 2, 3, 4. So 1.0, negative 1.0 times 10 to the 4th meters per second. That should be meters per second per second. So meters per second squared. That's your acceleration. Notice your acceleration is negative. Okay? Your initial velocity is positive. It switched direction. That means your acceleration is opposite in algebraic sign compared to your initial velocity. Your final velocity is negative in this case, since your initial velocity is positive. Okay? So that's how you would calculate acceleration. And we find applications of this in chemistry when we talk about pressures of gases. When molecules collide with walls, they exert a force on the wall. And then you divide that by the area of the wall, you get what's called the pressure. Okay? And you're constantly being bombarded with that just by being here. Okay? Air molecules, the molecules in the air around you, are constantly colliding with you, with your skin, and in the process, it exerts a force of the equivalent to about 14.7 pounds for every square inch of your body from the Earth's atmosphere. All right, so let's talk about force now. A force is a push or a pull. Okay, you're all familiar with the concept. And force is a vector also. So if force is exerted in one direction, if you're being pulled in one direction, you can say that the force on you is positive. If you're being pulled in the opposite direction, then the force on you is negative. And just like before, just like for the other vectors, it depends on which direction you take as positive or negative. Now, the sum of all the forces acting on you would be what you would call the net force. Okay? And the SI unit of force is called the Newton. It's 1 which is equivalent to 1 kilogram times meters times seconds squared. And in just a short while, we'll understand why that is the unit for force. Okay? Newton's laws allows us to explain motion, what we observe as the motion of objects, in terms of forces. Okay? And Newton's law basically says, first law says, that objects, the natural tendency for objects is to move at constant velocity. Okay, so that's called the law of inertia. The second law says if you see something accelerating, okay, then there must be an unbalanced force on that object, and the force that's on that object, okay, is equal to the mass of that object times acceleration. So if you have a particular object, if it's accelerating more, that means there's a stronger force acting on it. That makes sense. Yeah. Okay? Or if you have a bigger mass, okay, for the same amount of force, then your acceleration is going to be smaller. You won't be able to accelerate a bigger object with the same amount of force. Okay? And then the third law of motion says for every action there's an equal and opposite reaction. So if object 1 exerts a force on object 2, then that means object 2 is also exerting an equal force on object 1, and it's pointing in the opposite direction. Okay. So let's elaborate on those. Okay. Let's say you have a force of 5 newtons pushing an object to the right. So you have an object being pulled by a force of 5 newtons to the right. So I'm going to say positive direction. Okay, just make things easy. To the right, we'll take it positive. Going to the left, we'll take it as a negative direction. So a positive, yes? Okay. So if you're moving to the right with so there's a force pulling on an object 5 newtons going to the right, and a force of 7 newtons pulling it to the left. So the force going to the left is negative 7 newtons. What's the net force? You just add up the forces. So plus 5 newtons plus negative 7 newtons. Then that means negative 2 newtons is the net force. What do you expect to happen? You would expect, okay, acceleration is, force is mass times acceleration. So if you solve for acceleration, that's force divided by the mass. Okay, mass is always positive, so you expect the acceleration is going to be also a negative number in this case. In other words, if this object was already moving to the left to begin with, it's going to speed up to the left. Okay? It's going to accelerate to the left. So you're going to have a negative acceleration. If this object was moving to the right, if the object was moving to the right, the acceleration is going to be negative. Well, if you're moving to the right, if something's pulling you back, then that means you're going to have to slow down, right? So acceleration is negative. So force and acceleration have the same algebraic sign. All right. So Newton's law, like I said, is this equation right here. It relates force to the acceleration. Force equals mass times acceleration. So which will experience a greater acceleration if subjected to the same net force? A proton or an electron? What would it be? You're going to have to rewrite this. You want to compare acceleration. So acceleration is force over mass. Yes, the electron will experience a greater acceleration because for the same amount of force, a smaller m would be a smaller denominator. A smaller denominator makes the whole thing bigger, right? So whenever you're dividing something, you divide by a smaller number as opposed to dividing by a bigger number, you get a larger quantity. So an electron will be accelerated more. It's just like saying if you're going to push a kid, let's say a first grader, with the same force as you would push a 12th grader, then the first grader is going to experience a greater acceleration. Okay? All right. Direction of force. The direction of the force vector, like I said, is the same as the direction of the acceleration vector. So you'll notice here, if acceleration is negative, then the force is negative. If acceleration is positive, then the force is positive. So if you have an object that speeds up in a given direction, okay, then it's going to experience, the acceleration will be in that direction, okay, and it's going to experience a push or a pull in that direction. If it slows down while it's going in a particular direction, then the acceleration vector is pointing the other way, and so is the force vector. Okay. So here's a quick example. You have an object heading east, okay? Yeah, so here's east, and it's slowing down. What's the direction of the force? What would make it slow down? Which way should be the force pointing? West, correct. For it to slow down as it's moving east, there must be a force. So if this is your velocity, initial velocity, final velocity, that means your force must be this way. And so is your acceleration. So your acceleration, remember we said if it's slowing down, acceleration and velocity have opposite signs. And force and acceleration always have the same algebraic sign. Okay, here's a question. You have an object that's 10 kilograms. It falls to the earth in free fall. And we find that the object accelerates by 9.8 meters per second every second. So 9.8 meters per second per second. This thing is called the acceleration due to gravity. The earth is pulling the object down. What's the force on the object? So what we do here, the force is equal to mass times acceleration. And so the mass of our object is 10.0 kilograms. Our acceleration, okay, are we going to use positive or negative here? It doesn't matter. I want the downward direction to be positive, so I'll use positive. I want it negative, I'll use negative. Okay? So I'm just going to use positive. I'm just going to say the downward direction is the positive direction, so I'll just keep it at 9.8, positive 9.8 meters per second per second. So 9.8 meters per second squared. And so 10.0 times 9.8, 98. 2 sig figs, okay? Meters. Okay, so the unit here is kilogram times meters per second squared. So this unit right here, we can abbreviate that. That's a Newton. So we say that the downward force is 98 newtons. Okay? So you have 98 newtons of force acting on that object as it falls. Okay. For objects near the surface of the Earth, okay, the acceleration due to the Earth's pull is known as the acceleration due to gravity, as I mentioned earlier. It's about 9.8 meters per second squared. You can probably get a little bit more sig figs there, 9.80. And the magnitude of that force of gravity is what we call the weight of the object. So weight and mass, okay, are not the same. Mass is the amount of matter that you have in your sample. Weight is the force of gravity on the object. So in other words, if you want to quickly lose weight, you can go to the moon. You're not going to weigh as much there. You'll have the same mass. Okay? So weight is the force of the Earth or whatever planet you're on the object. All right. So that's why you may have noticed in some of your labs, there's a trend going on these days in chemistry labs in the instructions for the procedure to say mass the object instead of weigh the object. And that's just to emphasize the fact that mass and weight are not the same. Now, there's really nothing wrong with saying weigh the object, weigh 5 grams of that. There's nothing wrong with that. Because what you're really doing is when you're determining the mass in the lab, you're actually determining the weight, and you read that just gives you the mass. Okay, so you're just comparing weights. When you compare weights, you're comparing masses. So you can say, I don't think the word mass is officially accepted as a verb yet, at least not in the English dictionary. So in fact, the proper term is still to say weigh something rather than mass something. Okay. So what's the weight of a 0.5 kilogram book? The weight would be the force of gravity on that book. So mass times the acceleration, which in this particular case is g. So 0.50 kilograms times acceleration due to gravity is 9.8 meters per second squared. What's 0.5 times 98? 9.8. Half of 9.8 is 4.9 newtons. Okay. That's just the magnitude. I don't care whether it's positive or negative. That's just the absolute value. So weight is just the absolute value of the force of gravity. Now, how much force does the book exert on the Earth? So if you have this book, the Earth is pulling, so it's a half kilogram book. So that's about a 1 pound book. The Earth is pulling it down with a force of 4.9 newtons downward. Okay? How much force does the book exert on the Earth? So here's the Earth. Well, Newton's third law says that for every action, there's an equal and opposite reaction. If the Earth is pulling down on the book with a force of 4.9 newtons, then the book is pulling on the Earth with a force also 4.9 newtons directed in the opposite direction. Okay? So that's what the third law says. So you can think of it as the book pulling on the Earth with 4.9 newtons, or the Earth pulling on the book with 4.9 newtons. All right. Now, of course, when you observe things falling, they're not all going to be accelerating at 9.8 meters per second squared. And the reason for that has to do with the fact that they're falling through air. And that's the evidence that we have that there are molecules in air. So these molecules will collide with an object that's falling. And so the collisions between the air molecules and the object would tend to slow it down. So the net force exerted by all these air molecules, you call that air resistance, would be upward. It's against the force of gravity. So the net force that an object would feel is not exactly going to cause it to accelerate to 9.8 meters per second. The acceleration in general that you observe would be less. So that is evidence for the existence, that's one evidence for the existence of molecules. Okay, so the molecules will collide with the falling object, it retards the acceleration. But if you are to do this experiment in an air-free environment, drop things in an air-free environment, then you'll find that they all accelerate with the same amount, 9.8 meters per second. Now, let's say you have a table right here, and you have a book, okay, a 10 kilogram book. What did we say the force that the Earth exerts on this? 98 newtons, right? Okay. Now, so that's 98 newtons. What's the net force on the book? Well, the book's not moving, right? So velocity is 0. Acceleration is 0. Velocity is not changing. So what's the force on the book? Mass times acceleration, 0. Book's not moving. So there must be some other force that's counteracting that 98 newtons force that the Earth is exerting on the book. What's that? An upward force that's responsible, or that's doing it. So there must be a 9.8 newtons for 98 newton force acting on that book in the opposite direction, so that the total force on that book is 0. What's responsible for that? Upward force. there must be a force being exerted on that, and that force is due to the atoms right here at the boundary between the book and the table. You can only get your atoms so close, then they start to repel each other. Okay? So all of these atoms at the interface, at the boundary between the book and the table, you can only get them so close and they start to repel each other. So at the moment the repulsion between them balances the pull of gravity, that's when the book stops moving. Okay, so when it's not moving, that means you've reached a balance between the repulsive forces, okay, between the atoms at the surface and the pull of gravity on the book. So collectively, you refer to all of those forces as the normal force. That's what you call them in physics. But from an atomic perspective, that's really just atoms getting as close to each other as possible. They can't get any closer. Okay? So that's a chemical interpretation or atomic interpretation of that. In physics, you just call it normal force. Okay, 5 more minutes. Now, if you have a force that retards motion, that type of force is called a frictional force. For example, let's say you have a book. Again, let's put that book on a table. Okay? And you exert a force on that book that's 10 newtons. Okay, you try to pull it or you try to push it. What if the book doesn't move? If the book doesn't move, then the net force must be 0. So that means there must be an opposing force of negative 10 newtons. So that opposing force, you call that the frictional force. Where does that come from? Again, that has to do with the interactions of the atoms at the boundary between the book and the table. Okay? There's a resistance to atoms. You're going to encounter resistance when atoms try to slide past each other. So there must be some kind of interaction between the atoms at the boundary between the book and the table. Now, the forces in nature, okay, can be classified into 4 fundamental types. Gravitational, okay, and that's what causes objects to fall to the earth. Okay, and that's what causes the force between planets that's present between any pair of particles. Electromagnetic, strong and weak. Now, strong and weak forces, they are only significant at very, very short distance, like between the protons and neutrons in an atom's nucleus. Okay, so we're not going to be too concerned about those. Gravitational force, like I said, depends on the masses of the objects and distance between them. And electromagnetic force, this is really the most important type of force we deal with in chemistry. Okay, because these are the forces that charged particles exert on each other. So these are the forces that protons and electrons exert on each other. So interactions of atoms and molecules, if you want to understand the interaction of atoms and molecules, the movement of atoms and molecules, how they behave, you have to understand electromagnetic force. Okay? So that is primarily the type of force that we deal with in chemistry. Okay? Now, if you have a comparison, if you've had some physics, there's a formula for the gravitational force. It's equal to some constant g right here times the mass of the product of the mass of the objects and the square of the distance between them. Okay, electromagnetic force can be coulombic or electrostatic or magnetic. The electrostatic force, okay, which depends on the charge of the particles and the distance between them, is given by what's known as Coulomb's law. Basically, what this says is the higher the charges, the stronger the force. The farther they are from each other, the weaker the force. Okay, your r squared here is in the denominator. Now, magnetic force is also something that's associated with charged particles. It's something that's generated when charged particles move. Okay, and it affects moving charged particles. So what we physically experience as magnetic forces are actually due to charged particles. Okay, protons and electrons, just by being protons and electrons, they are in fact, magnets. They have what's called intrinsic magnetism because of what's known as a spin. We'll talk more about that later in the semester. Okay, so those are the types of forces that we encounter. And if you were to compare the Coulombic force, for example, and the gravitational force in the case of hydrogen, if you use that formula we had earlier, okay, you'll find that the gravitational force between a proton and an electron is 3.6 at a typical distance. The average, most probable distance of an electron from a proton in a hydrogen atom is about 52.9 picometer. Picometer is 10 to the negative 12 meters. Okay, so at that typical distance, the gravitational force between them is 3.63 times 10 to the negative 47. That's a very small force. Whereas the Coulombic or electrostatic is 8.25 times 10 to the negative 8. Well, how does 10 to the negative 8 compare to 10 to the negative 47? That's about versus 10 to the negative 47. So 47 minus 8, that's 39. So that's about 10 to the 39 times stronger. So electromagnetic force, the Coulombic force, is 10 to the 39. That's 1 followed by 39 zeros times stronger than the gravitational force. So pretty much when you're dealing with interactions of atoms and molecules, at that level we can ignore gravitational forces. We're just going to be focusing on the electrostatic forces between them. Okay, I think this is a good time to stop.